Okay? So I need you to stop talking, please. All right. So which one of these polynomials do you want to talk about? Let's do two.
Number 2. 2 4.
Well, okay, so I'm going to go through all the parts. These are the four polynomials. 2, fine. What other one do you want to look at?
And 4.
4? Okay. Sounds good. All right. So I'm going to do all the parts for each one of these two polynomials, okay? So for example, like that means this is 2. It also means we're doing 6. It also means we're doing 10 and 14. Similarly here, it means we're doing 4, we're doing 8, we're doing 12, and we're doing 16. Okay? You guys get what I mean there? Okay. All right. So let's just start by looking at this first polynomial. So the first thing I want to do is list my possible rational solutions. So that's going to be the factors of 24 divided by the factors of 2. So the factors of 24 are plus or minus 1, 2, 3, 4, 6, 12, and 24. And then if I divide each of these by 2, I get 1/2. If I divide 2 by 2, I get 1, which is already on my list. If I divide 3 by 2, I get 3/2. If I divide 4, 6, 12, or 24 by 2, I still get something on my list, so I'm not going to include those. So this should be your answer for number 2. Now, if you had this in a different order, that's fine. If you didn't reduce, that's fine. If you had the duplicates, I'd prefer not. Sorry, 8. 3's on there. I guess I did forget to write down 8. Thank you. My apologies. Okay. The next thing I'm going to do is I'm going to look at the graph. So if I type this in, I have 2x to the 4th plus 5x cubed minus 16x squared minus 10x plus 24. Okay, I'll go to my window. I'll set my window to maybe negative 25 to positive 25. I'll probably need to zoom in again, but that'll at least be my starting spot because those are the biggest and smallest answers from my, or a little bit bigger than the biggest and a little bit smaller than the smallest from my list that I just made there a moment ago. So I hit graph. Okay, so it looks like everything's happening between like, I don't know, maybe -5 and then +3 or something. So I'll just take a guess. I see potentially 3 x-intercepts. So I'm just kind of guessing at that or approximating. So here's -5 to +3. So it looks like, let's see here, this is 0, so this is -1, -2, -3. So that's probably -4. This is probably -1.5. And if I do the positive side, that's +1, +2. That's probably +1.5. Is everybody okay with that idea? So far, so good? Okay. So that was like, what was that? That was like number 6 that we just did there. So moving on to 10. Here I'm doing the synthetic divisions to do my factoring. If I compare the values from my graph to the values on my list, I see that it appears that all of them are there, right? At least at first glance, it appears that's what's going on, okay? So I can start my synthetic division potentially with any one of these three. Now, I'm not going to use any one of these three. I'm going to pick the -4 because it just makes the arithmetic much, much easier. And it's the one I feel the best about. Obviously, the other ones I did more estimating on since they were decimal. I mean, it's tough to tell the difference between like 1.4 and 1.5, right? It's a lot easier to tell if it's exactly 4 where it's like on the tick mark. So that worked. So what that tells me then is because -4 gives me a remainder of 0, x plus 4 is a factor, and then my other factor can come from this stuff. So that's going to be 2x cubed minus 3x squared minus 4x plus 6. And now I can do two things here. I can try to synthetically divide again, or I can try to factor this polynomial. Probably some of us tried to do synthetic division again. It looked like that happened on a lot of your guys' sheets, and you got something that didn't work when you tried -1.5. Right? Tom?
Would you divide -4 by 2?
Why would I divide it by 2?
I don't know, because you just said that in one of the examples you fit over 1.
Yeah, that's what we did back here. We have -4 over 1.
I don't want it to be
and -4 over 2 is right here.
the leading coefficient is 2, right?
Right.
Divided by 2 or no?
Yeah, so we have to do both of them. So if you go back to what we showed you guys yesterday, you have to do everything over here, and this one, and then everything also over that one, right? Okay with that, Tom? So I need both. I need 4 over 1 and I need 4 over 2.
Okay.
Right? Now, I didn't include 4 over 2 on my list because it was already on my list. 4 over 2 is just 2. So I didn't write it a second time.
Oh,
Okay? But 4 over 2 is nowhere here. So I don't know why we're concerned about -2 or +2 because it's not on the list at all.
I thought you divided the leading. I thought you divided the one of the graph numbers by the leading coefficient.
No, the graph numbers are the graph numbers. Those don't you don't change those at all. Okay?
Okay.
Okay. So who here tried to do synthetic division a second time on this problem? Great. And when you tried to do that, did you use -1.5? No. Okay? Did anybody try using -1.5 when they did the synthetic division a second time on this problem? Jack, you did. What happened? It didn't work. You got a remainder of non-zero. What does that tell us then? Did Jack make a mistake? Not necessarily, right? What could be going on here? This -1.5 is not a rational number. It's actually irrational. So it's something like maybe it was the square root of 2 or the square root of 3 or the square root of something, right? It's some non-fractional number here. That's okay. So if that happened, you could now move on and try +1.5, or, and this is what I'm going to do, is I see this and this is factorable by grouping. That's what I'm going to do here. Jack, are you okay with the explanation I gave there as to what's going on? So not necessarily have you done anything wrong. So I'm just going to factor this by grouping because it's got 4 terms And if I look at it kind of carefully, I can see that it's going to be factorable by grouping. From the first group, I can take out an x squared. And from the second group, I can take out a negative 2. I notice then each of those has a 2x minus 3 in it. So when I take that out, I'm left with an x squared minus 2. And then that x plus 4 still comes down along for the ride. Annalise. Okay.
What happens if you take out a 2x?
So if you're getting to this step and these two are different factors, one of two things has happened. Either maybe you haven't taken out as much as you can, right? So it could be possible that you just didn't factor out the right stuff to make them the same. What's more likely to happen, though, is that this would not be factorable by grouping. In which case, then, there would be some factor on the list that should work for us. Okay? We're not guaranteed that there is, but I saw this and this was factorable by grouping, so I stopped dividing here and just did it by grouping. And there is another number that is going to work. It would have been positive 1.5. Had you tried doing that, it would have worked.
Yeah, I thought it was
Okay.
So
you wouldn't have done anything with that, right?
Yeah.
So you would have had to do this by grouping, right? Okay. And then the last step is the solving step. Because we have this in factored form, the solving is quite easy because all we need to do now is set each factor equal to 0. And then I can solve each of these factors independently. So I have negative 4. If I add 3 and divide by 2, I have positive 3 over 2. If I add 2 to both sides and then square root both sides, I'm going to get the plus or minus square root 2. How many answers do I have listed here? I have 4, right? I have negative 4, positive 3 over 2, positive square root of 2, and then also negative square root of 2. If I type the negative or the square root of 2 into my calculator, that's about 1.41. How come I see 4 answers here, but I only saw 3 x-intercepts on my picture? That's curious, right? Well, what has happened is positive 1.5 and positive 1.41, those are very close together. Let's go and zoom into that area of the picture. So I'm going to zoom in very close to here. I'm going to go from 1.3 to 1.6. And that's going to zoom into that one part of the graph. If I do this, I'm going to have to change the y's also. Let's do that real quick. So if I do that, I can see that there are actually 2 x-intercepts going on at that little dip. Now that was very hard to see. Do you guys get what I mean? So that part that looked like it was just hitting the x-axis and turning around, there was actually 2 x-intercepts hiding in there. Now, from looking at the graph, would I suspect that? No. I probably wouldn't have figured that out until I got the solutions mapped out. And we're going to add on some things, some more tools that we can use to help us detect that kind of a situation, or the possibility of that situation. John. I typed in the square root of 2 into my calculator and got the decimal. All right. The other one we wanted to look at was 4, right? All right, so the first, my rational roots theorem, my list of possible rational zeros is pretty long, but it's not so bad because at least it's only the factors of 108, since the only factor of 1 is 1, and anything divided by 1 is itself. I just have a lot of them. Any questions on that? Okay. Next up, I'm going to go to the graph here. So I have x to the 5th plus 5x to the 4th minus 5x to the 3rd minus 45x squared plus 108. I'm going to go choose my window. I'm going to pick something a little bit smaller than my smallest one, so maybe negative 110, and a little bit bigger than my biggest one. And I'm going to change my y min and y max back to negative 10 and positive 10. I'm going to hit graph. Now watch carefully. Did you see that pop up? How the y-axis appeared to get a little darker for a second there? That's the graph graphing. Our window is way, way, way too wide to see what's going on here. So I'm going to go ahead and change my window. Not surprisingly, given that 108 is a gigantic value there. I'm going to just zoom this down to -5 and +5. And I should get a much better picture. That's much more reasonable, right? John? I just guessed to zoom it down. I just cut some of it off. Since before it was like mostly empty, the only stuff that would have been going on would have been the stuff near the y-axis. So instead of looking at, I just zoomed it into -5 and +5. Because most of it was empty, right? That's all. I just took a guess. If you had picked -10 and +10, it probably would have been fine. You know what I mean? You just need to leave some space near the y-axis there so you can see what's going on. All right. So what 2x intercepts do you guys see? Yeah, 2 and -3. I agree. Okay. If I look at my list, both of them are there, right? So both would be good candidates to start my synthetic division with. Which one do you want to start with? -3, sure. The people that, I shouldn't say that yet. I don't really remember when I did this, if that works. Oops, I almost made a mistake. What mistake did I almost make? Got to have that 0 there. Why am I putting a 0 there? Because I skipped the regular x's. Yeah, so if you had trouble getting the synthetic division to work on this, that's likely was the problem. All right, let's get this rolling then. So that worked. What I have now is still a 5-term polynomial. I don't have any way to factor that with the factoring tree, so what should I do next? Another synthetic division. Good. With what value? 2. Okay. That worked again. All right. So it appears that I'm done here. The problem is if you try to factor this by grouping, does it work? No. What should I do? Do what? Flip this. No, doing it in reverse order I don't think is going to help you. Here's what you do. How do I know that -3 and +2 are only used one time? How do I know it wasn't something that like x plus 3 times x plus 3 times x plus 3 times x plus 3 times x minus 2? How do I know that those factors are used only once? We don't, do we? And because we're out of factors to try, and we still have something we can't factor by the factoring tree, let's try doing one of them again. Either -3 or +2. Let's just pick one. Sound good? You got a choice? What do you want to do? 2. Great. Sounds good. It worked. At this point, we're left with a quadratic down there, right? It has 3 terms. That we should be able to factor by hand if it's factorable at all. So, because the -3 gave us remainder 0, I have a factor of x plus 3. Because 2 gave us a remainder 0, I have a factor of x minus 2. Because we had 2 that give us a remainder 0, I have another factor of x minus 2. And then that stuff is x squared plus 6x plus 9. Annalise. This is the constant term, the x coefficient, the x squared coefficient, right? Juan?
So, the first time
Yeah, so that's basically what the synthetic division does, is each time it makes the polynomial you're trying to factor a little 1 degree smaller. Yes. Well, right, exactly. So I had 4-term polynomial. I looked at it for a moment, and I saw that it wasn't going to be groupable. You might have had to try to group it and still been unsuccessful. So I knew that it has to still be able to factor. I don't know that 2 and -3 only are used one time. They could be used more than one. We'll actually talk today about, or maybe it won't be until next time, but we'll talk about how to give us a clue as to when that's going to happen. Because there is a clue. Sure, there's no reason to not have tried -3 at this point. We don't know. Annalise.
Like, the one we did like last time, it was like all 4, like we did this and like. And then like I couldn't have done it, like I got 1 point.
Right.
So like if I had only done like one synthetic division and then I thought like that, like oh no, I couldn't get factored by everything.
You could have tried, it wouldn't have worked though, because 4 only appeared as a factor once in the problem. So yes, that would have not been a terrible idea. It wouldn't have worked in the previous problem, but you could have tried it. And again, we're going to talk about how you can tell whether something could be used more than one time, either today or next time, depending on how far we're able to get. But that's an important clue. And it's something we can get some intuition about before we even start synthetically dividing. Mm-hmm. Yeah. So the goal about all the theorems we're getting is to reduce the guessings. Okay. So x squared plus 6x plus 9, that factors also. What does that factor to? Yeah. 3 and 3 are the 2 numbers that multiply to give us 9 and add to give us 6. So I'd have another x plus 3 times x plus 3 at the end. So in this problem, either 2 or -3 would have worked a second time. And really, the way we would probably write our factored form for this is we kind of write it this way. Instead of writing 3x plus 3s, we'll just write as x plus 3 cubed. And instead of writing 2x minus 2s, we just write x minus 2 squared. So here's our factored form. And then to solve, we just set these things equal to 0, right? So when I set x plus 3 equal to 0, I have to set it equal to 0 3 times. And when I set x minus 2 equal to 0, I have to set it equal to 0 twice. So I get negative 3 as an answer 3 times. And I get positive 2 as an answer twice. So when we have an answer, a solution like this that appears more than once, we call it a multiplicity. So the first solution, we say x is equal to negative 3 multiplicity 3, meaning that solution can occur 3 times. And similarly, we'd say the second solution is x equals 2 multiplicity 2, indicating that that solution occurs 2 times. Do we feel a bit better about the homework? Some of the weird things that you saw happening now, hopefully we feel a little bit better about. And it was a little bit of a, again, I didn't really expect any of you guys to be able to do that fourth one. I expected to come with a bunch of questions about it. And I expected you guys to come with a bunch of questions about 2. Because again, there were things in there that maybe we weren't that prepared to deal with, right? The presence of irrational roots and the presence of multiple solutions potentially cause us a lot of problems, right? So we can do a little bit better even to this procedure than what we've established so far. So the pieces that we're going to add on to this procedure, these new theorems that I'm going to introduce today, are going to be simply, or are only going to be used in this pre-synthetic division part. They're not going to change the ending of the procedure where we synthetically divide to factor and then set those factors equal to 0 and solve. It's only going to tell us about like when some of these weird things can happen. Okay? All right. So this first theorem is the fundamental theorem of algebra. And this just says that all polynomial equations have solutions in the complex numbers. So basically, all it's saying is that any polynomial equation you can write is solvable. Doesn't tell you how to solve it, doesn't give you any intuition about solving it, but it says that you're not wasting your time trying to do something that's impossible. They're all possible. For our purposes, though, not tremendously helpful. We have a corollary to this. A corollary is just like a theorem that uses another, like is a, uses another theorem more specifically. And I'm going to abbreviate the fundamental theorem of algebra just as FTA. So the corollary says the number of solutions to a polynomial equation with integer coefficients is going to be the same as the degree of the polynomial. Now you'll notice that I've underlined and starred the same. And the reason I put the asterisk there is it's only the same if you count the multiple solutions and you count the imaginary solutions. So if you count everything, then the degree is the same as the number of solutions. But you got to count all the solutions, regardless of whether they're used multiple times and regardless of whether they are real or imaginary. The primary use to this corollary is it tells you like when you're done, if you found everything. In particular, we can use it to check for imaginary solutions. So I should be able to look at the graph, count my x-intercepts, and tell if it's possible to have imaginary solutions or not. If it's a degree 3 polynomial and I see 3 x-intercepts, I can't have imaginary solutions, right? Because I see 3 solutions there. If I have a degree 5 polynomial and I see 3 x-intercepts, it's possible that I could have imaginary solutions there. It could also be possible I have a duplicate, like a solution that's used more than once going on as well. So, but that's the idea. The next theorem is called the bend, bounce, straight theorem. So, if the x-intercept in the graph of a polynomial with integer coefficients, 1, yes? Yeah, I'm recording. So if the x-intercept in the graph of a polynomial with integer coefficients, 1, passes straight through the x-axis, that solution would be used one time. Exactly once. If we have a bounce at the x-axis, that solution could be used an even number of times greater than or equal to 2. So it could be 2 times or 4 times or 6 times or 8 times. And there's an upper bound. What's the upper limit to the number of times it could be used? Not infinite. It's capped by the corollary to the fundamental theorem of algebra, because we know how many solutions the polynomial can have. So we couldn't have a multiple solution that's used more than the number of total solutions, right? If I have 5 solutions that I'm looking for, you could be used 2 times or 4 times, but you can't be used 6 times because there's only 5 solutions possible.
How do we find that solution?
It's the same as the degree.
Oh.
And a bend, that solution could be used an odd number of times greater than or equal to 3. So 3 times, 5 times, 7 times, etc. And that's capped by the fundamental theorem of algebra. So the question becomes, what do these things look like? Bend, bounces, and straights, right? That's the next question. Yes, Tom.
How do we know how many solutions each equation has?
That's the same as the degree.
I know, but like, what would we do if we needed like 2 solutions?
We'll do some examples here that incorporate this at the end. I'm just kind of presenting these rules out here. And they're not going to do much. All of the things that I'm doing here are really things that I'm going to do when I look at the graph. So I'm not going to do much computationally. They're just going to help me when I'm looking at the graph and making decisions about how to synthetically divide and what things to synthetically divide with and how many times to do that synthetic divisions. Grace. Yes. Massimo. You may. All right. So here's a graph of a polynomial. That x-intercept is straight. If I look at just that little piece of the graph, it goes straight through the x-axis. Everybody see that? This x-intercept is a bounce. If I look at just that little piece of the graph, it looks like it hits the x-axis and then bounces back the direction it came from, right? This one is a bend. Again, if I look just at that little piece of the x-axis, you see how like one part of it was like kind of half of a polynomial or half of a quadratic, and the other half was like the other half of a quadratic. How one side of the graph is like scooping up and the other half is scooping down. Did you guys see that? That's what we mean by a bend. So if we looked at that polynomial in number 4, if I look at the graph, this is a bend, right? This was a bounce. When we go back and we looked at the answer that we got there, -3 was used 3 times. +2 was used 2 times. -3, there was a bend. +2, there was a bounce. This is nice, right? It helps us right at the beginning when we look at the graph immediately know when I might be using one of these more than once, right? There would have been no ambiguity at the beginning about what to do. You would have known right away, okay, I can divide 2 at least 2 times. I can divide 3 at least 3 times. So I could keep going until I found something that was factorable, or until I used it up, basically. Okay with that? All right. Two more theorems. The next one is called the Irrational Conjugates theorem. So the irrational conjugates theorem says in a polynomial equation with integer coefficients, irrational solutions occur in conjugate pairs. What do I mean by a conjugate pair? Well, for example, square root 2 and negative square root 2 are conjugate pairs. Or 1 plus the square root of 3 and 1 minus the square root of 3 are conjugate pairs. Or 7 minus 2 root 6 and 7 plus 2 root 6 are conjugate pairs. Basically, it means that the symbol in front of the radical is the opposites. That's what we mean by conjugate pairs. Is everybody okay with that idea? Knowing this would have been helpful doing that problem number 2 from the last night's homework. Because when you tried to divide negative 1.5 and you found that it didn't work, it told you it was irrational, which would have told you there's another irrational one lurking somewhere. The only candidate would have been out there at positive 1.5, in which case you would have been missing another solution somewhere, and you would have likely gone to zoom in and found that, hey, there's actually 2 things there, and maybe come up with positive 1.5 would have been a rational solution you could have done synthetic division with. And our last one is the complex conjugates theorem. So in a polynomial with integer coefficients, imaginary solutions occur in conjugate pairs. And again, what do we mean by conjugate pairs for imaginary solutions? Well, things like I and negative I would be a conjugate pair. Or 2 plus 3i and 2 minus 3i are conjugate pairs. Or 7 minus 1/2 I and 7 plus 1/2 I are conjugate pairs. So I'm going to give you guys this handout. We're going to do number 1 here together. If we run out of time and can't finish number 1, we'll finish it next time we meet, and your assignment obviously wouldn't be due until the next class after that. All right. So looking at this, we're going to do number 1 here together. So here's our polynomial, right? How many solutions should this have?
5.
5. How'd you get that?
So one thing.
It's the degree. Good. Use the rational roots theorem to come up with your list of possible rational solutions. So it's going to be factors of this, divide by factors of that. So we just have plus or minus 1, 2, 4, and 8. Everybody okay there? Use your calculator to identify the likely real solutions. So I'll fire up my calculator here. All right, it just wants to be difficult. I have x to the 5th minus 4x to the 4th plus x cubed plus 10x squared minus 4x minus 8. I'll graph that from negative 10 to positive 10 because that's a little bit smaller than my smallest and a little bit bigger than my biggest. Solution from my list there. So if I look, it looks like negative 1 and positive 2 are my two x-intercepts. You guys agree with that? It says compare your answers for B and C to identify any likely irrational solutions. So what I notice, negative 1 is on my list and positive 2 is on my list. So likely I have no irrational solutions, right? I only see two x-intercepts. They're both on my list. Shouldn't be any irrational solutions. E says use the bend-bound straight theorem to determine the number of times each solution can occur. So, negative 1 is a bounce. Everybody agree with that? So that means we could be used an even number of times. I could be used 2 times. I could be used 4 times. But I can't be bigger than 5 because that's the maximum number of solutions I can have. Positive 2 is a bend, right? So that could be used 3 times, or it could be used 5 times. Now, is it really possible that x equals 2 is used 5 times?
No.
No, because I know that negative 1 is used at least 4 or at least 2 times. Could negative 1 be used 4 times? No, because x equals 2 has to be used at least 3 times. 4 and 3 would be too many. That would be 7. Everybody agree with that? I'm actually have started doing F. My apologies. So F. This is the table that I'm going to make. The total is always going to be 5. Because that's the total number of solutions I can have, right? For this problem. The irrationals, we already established as 0. Because there was, the only x-intercepts we saw were things that were on our list. Negative 1 could only be used 2 times. Negative or positive 2 could only be used 3 times. 2 plus 3 is exactly 5, leaving no room for imaginaries. So this is my only possibility. In some of the problems 2, 3, and 4, you'll have more than one possibility in your table. Okay? That can happen. So G then says, let's use synthetic division to factor the polynomial. So I'm going to just start with positive 2 to do my synthetic division with. It doesn't really matter which one you picked. And I'm just going to divide this a couple of times, right? How many times could I use this? I could use it how many times? 3. So let's use it all 3 of those times and see what happens. So each time I'm getting that remainder 0, right? That's good. That worked. What could I do now? I could switch to -1, or I can try to factor this since it's just 3 terms. I know it's a quadratic, and that should be easily factorable. Let's actually do that. So I have x minus 2 that's used 3 times. And then I have the quadratic x squared plus 2x plus 1. That should be easy to factor, right? What multiplies to give us 1 and adds to give us 2? 1 and 1. So I'd have x plus 1, and since I have it there twice, I can just write it as x plus 1 squared. And then h, to solve this, I'm just going to take my factored form and then set each of the pieces equal to 0. So I get 2 3 times, and I get -1 2 times. And that's it. So again, the process that we outlined in the last homework assignment didn't really change here, right? It's just that when we looked at the graph, we had some other things to consider so that we could make some more informed choices about what to use to do the synthetic division. So I'd ask you to finish the other 2 problems here on the sheet for next time. And if you have any backlogged homework that you still owe me, please try to get that taken care of. Thanks, guys. Have a good weekend.